Hello and welcome to this manufacturing process technology part 2 module 12. We were talking about the USM process, the ultrasonic machining process and the Shaw theory related to the material removal estimation through a geometrical model. So, in this model the direct impact of the tool on the grains in contact is considered separately, and then there is another module which is constructed by assuming that there is a grain throw case where the grain comes and hits into the tool, and then by virtue of the momentum transfer of the fast moving tool, the grain is impinged onto the workpiece surface and it hits the surface and creates a fracture. So, there are two different ways. One is a direct ploughing or a direct hammering. The second case is where the grain makes an impact by just a free throw of the grain between the gap created by the vibrating USM tool and the workpiece. So, the assumptions that are made are that the rate of work material removal is proportional to the volume of the work material removed per impact. The rate of the work material removal also is proportional to the number of particles making impact per cycle, and again the MRR is proportional to the frequency of the tool head, that means the number of impacts made by the tool per unit time or number of cycles that are associated with the tool per unit time. And then we assume certain other basic things like the identical nature of all impacts and the abrasive grains and by and large identified to be spherical in shape, although they are not truly spherical. Abrasives are really sharp edged grains, and then obviously the material removal also to a large extent depends on that sharp edge of the grain. But in this particular case, just for geometrical assumption and just for derive something more simplistically, we assume all the grains to be spherical and creating brittle fracture just by penetrating perpendicular to the workpiece surface. So, these are some of the assumptions that Shaw makes in order to find out at least the order of magnitude estimation of various parameters related to the USM process. So, typically if we look at it mathematically, the material removal rate Q is proportional to volume of the work material removal per impact, proportional to the number of particles making impact per cycle, and then the cycles per second or frequency at which the tool is making impact. So, it is V Z nu which is proportional to the work material removal Q. Let us assume that there is a case where there is an abrasive particle, a spherical particle which is impinging onto a work surface, as you can see in this figure right here. The diameter of the abrasive grain is assumed to be small d, and the total diameter of the area which gets affected because of such an impact at a certain point of time when the depth of penetration of the abrasive grain is h is given by d. So, it is basically a circular area on the surface which gets affected, which is a projection of this abrasive spherical grain, and the diameter of the circle on the work surface is given by capital D. So, having said that, now let us consider this impact of this rigid spherical abrasive grain on the work surface, and what is the geometric relationship that exists between the various parameters which are mentioned here to maybe work out some active relationship with the material properties and the material removal rate. So, the figure on the right shows right here shows the indentation caused by such an impact. If capital D is the diameter of the indentation at any instance, then, and also we assume that h the corresponding depth of penetration, then we get that capital D by 2 is really equal to the small d by 2, that is the mean abrasive grain diameter here, minus of d by 2 minus h square. That is how you can relate this length here is d by 2 minus the length h, which is happening here because of the depth of penetration. And so typically this OAB is a right angle triangle. So this is square, or the square of this length is actually equal to square of this length minus square of this particular length d by 2 minus h. So that is how you get the value of the indentation diameter d. In other words, we can get d to be equal to 4dh minus 4h square, and as the depth of penetration h is very small in comparison to at least the projection of the diameter or the grain diameter, or even the average grain diameter itself. Probably it's a tenth of what the average grain diameter is, which is correspondingly which is actually about 15 to 20 or even beyond 15 to 50 microns in range. So this d is the average diameter of abrasive grain. So therefore capital D becomes equal to twice root d of h, and that is how you get your first relationship here, which talks about how the indentation diameter can be related to the diameter and the depth of penetration of the grain. Okay. So assuming the volume of material dislodged per impact to be proportional to the d cube, we very easily get q from Shaw's theorem to be equal to the volume that is involved, that is dh to the power of 3 by 2 u. Remember, twice dh whole under the root was what the diameter d, capital D was supposed to be. So obviously the two factor is of course a constant of proportionality, so we can take it off, and then we have z times of v, which creates this factor MRRQ. So since the mean speed of the tool is low, the mean static feed force F applied to the tool must be equal to the mean force of the tool on the grains in any event. The tool is so heavy in comparison to the grains that it is almost a direct momentum transfer of the tool, and the grain mass does not really create any kind of inertial impacts on back to the tool. Okay. So the D'Alembert's force given by the grain mass onto the tool is much smaller, and it is almost a direct transition of the momentum of the tool onto the workpiece onto the grains because of the much heavier mass of the tool in comparison to the grains. Okay. So it is almost a direct transfer. You could consider the mean static force F applied to the tool must be equal to the mean force of the tool on the grains directly. So when the duration of an impact is about, let us say, small delta t, and the maximum value of the impact force Fi is Fi max, the nature of variation of the force F with time can be the following. Okay. So, let us look at how this variation of F would be. So, typically the force is starting at some point along the cycle of the whole grain impingement process, and if the cycle of the, so the tool, if you look at the tool, it basically starts from a mean position, starts going towards the workpiece, and until it squeezes the grain between the tool surface and the workpiece surface, the force on the grain can be 0, because the grain is moving exactly in the direction of the tool. But with this time period on board, or with this as a part of the total time period of oscillation of the tool, there is a substantial amount of path length where the force felt on the workpiece is almost 0, because the grain has not yet touched. But when the grain has actually started touching, and now it is giving a reverse reaction, so that is really where the force comes into picture. And so obviously as the tool progresses and the grain kind of impinges onto the workpiece, the force by the grain onto the workpiece keeps on increasing to an extent where it is able to cross over the ultimate yield stress of the material. Okay. And beyond that, there is a fracture. So the grain and the fractured piece gets dislodged automatically, and the force comes down to 0. So that is how you basically representing this trend here, that the force at certain point of time when the grain has started pressing, let us say at this particular point A, is starting to increase all the way up to a maximum force Fi max, beyond which there is a flow stress which comes into the material, and there is a fracture and a failure, and beyond that the force again comes back to 0, because now you can think of as if the tool is also receding away. That is because obviously it is coming to the extreme position and then again returning back to the mean position, and at the same time because of the dislodgement and everything else, there is a cavity now, and the fractured piece as well as the grain has moved off. So there is no force, active force on the workpiece anymore, unless the next grain comes into picture, unless there is a another such interaction between the tool head and the grain which impinges. So in one particular cycle, when there is one near proximity of the tool to the workpiece, and again going back to the mean position, you should have at least one. If you consider only one grain to be squeezed between the workpiece and the tool, there should be one such force starting from 0 all the way to Fi max, and then back to again the point B, where really there is no contact again of the grain to the tool. The tool and the grain and the dislodgement has flown away. You have to remember that there is a high pressure slurry which you are injecting, which has a carrier medium which would be able to dislocate every dislodged piece from the workpiece, coming off the workpiece because of the brittle fracture process. Okay. So that is how one time cycle of force could be shown. So the average force, therefore the average force here given by capital F is actually 1 by t, t being the time period, times of the integral 0 to t Fit dt. Okay. So it is the time integral of force divided by the whole time period t as the average force. So where capital T is the time period of each cycle. So you can think of this as the area under the force time curve averaged out over the whole domain of the time period t, which we are considering for this operation. So the duration of the impact is actually delta t, as can be seen here, and the maximum force is Fi max. So, it will not be erroneous to assume this nature here of the force to be triangular, meaning thereby that I mean I can actually be able to estimate the area under this curve as the area of the triangle half Fi max delta t. So, that is how I can estimate the area under the curve given through this expression 0 to t Fi t dt. And so, you can understand this is half base altitude being Fi max and again base being delta t. And so, if I divide that by the time period t, I get the average force F average in this situation. So, this is only an approximation however, and it works very well because obviously this peak is very sharp. So, it goes all the way to an extent where the ultimate yield strength just gets exceeded and then there is a fracture initiated. So, there is a sudden reversal of the force. So, it is quite sharp and quite high quality when we talk about the force time trend as in this particular case. So, now if you look at the way that the tool really positions itself, the tool let us say is about a mean position O, and the position A indicates the instance that the tool face touches the abrasive grain. So, the grain is somewhere here lying in touch with the workpiece on one side, and the tool moves between O and A. So, that the tool starts pressing the grain. The period of movement from A to B represents the impact, because now it has to go all the way up to the indented value which is B here. So, this surface moves to B all the way, meaning thereby that the grain would actually now move without breaking into the workpiece, and AB is really the distance that it would cover like an indentation onto the grain onto the workpiece surface. So, the indentations caused by the grain are both on the tool as well as the work surface. You can think of it here that instead of looking at only the workpiece, if I also were to find out, obviously the grain is much harder than the tool as well. So, there is some depth of indentation on the tool side, we call this HT, and some on the workpiece side HW, and obviously the ratio of hardnesses of the tool surface to the workpiece is very important and is quite matterable whenever we talk about the EOSM process. Okay. So, beyond this position B, the tool recedes back, passes again through the mean position O, go all the way up to another extreme position C, and then comes back to O. So, this is how the whole tool oscillates back and forth about the mean position O when we are talking about particularly a ultrasonic frequency at which it does so. So, then the total amount of indentation, the total indentation as can be seen right here in the figure, is actually given by the total indentation on the tool side plus the total indentation on the workpiece side. Okay. So, I can always write this as HW is indentation caused in the work, and HT is that caused in the tool side. Okay. Supposing that A was the amplitude of oscillation in this particular case, the total time of oscillation from the mean position O to C back to O, again O to B and again back to O, if that is equal to time period t, the average velocity therefore of the tool is exactly 1/4 cycle having amplitude A divided by t by 4. So, you have 4A by t as the average velocity of the tool head, which you get realized because of this fast moving. You have to think of it that the amplitude A is basically from mean to the extreme position, and in the whole time period t you are covering at least 4 such amplitude movements about the mean position. So, having said that, now the total time needed, if I wanted to calculate to move the total indentation distance, that is h, should be equal to h divided by the average velocity of the tool. So, in other words, it is actually h divided by 4A by time period t, and h can already be supplemented with the tool workpiece indentations times of t by 4. So, that is how the average velocity, that is how the total time delta t that is needed to move the distance delta h or to move the distance h is represented. Okay. So, mind you, again this h is composed of the indentation across the tool as well as the workpiece. So, the average force on the other hand, as we had calculated earlier, is actually equal to half Fi max times of the time delta t, which I had just calculated. Time delta t is obviously the time in which the grain gets indented. So, I just substitute this value h t plus h w divided by A times of t by 4 times of 1 by t. That is how the average force was represented. If you may look at, the average force here was half times of Fi max times of delta t, which is actually the total time period needed for the force cycle to go to Fi max and back in the graph earlier. So, having said that, now the Fi max therefore can be represented as 8 times the average force times the amplitude divided by h w plus h t. The whole goal behind what we are trying to do here is this Fi max can be very easily correlated, if we knew the area of the indentation, to the ultimate yield strength of the material, which is actually a property. So, with that on board, we would like to do something so that we have now a very important estimate of what is going to be the average force, what is going to be the amplitude. Obviously, the depth of indentation can also be studied by looking at the various features on the surface which get formulated, and so that is how I would like to bring in something related to the property and something related to the geometry to sort of predict what is going to be, at least order of magnitude wise, the material removal rate. So, it should be remembered that during the period delta t around z grains are in simultaneous contact with workpiece, and they are all being simultaneously plowed into the workpiece by the tool head, and so the force per unit grain is represented by the Fi max per unit z. Okay. So, the approximate area of contact of the work surface per grain, you can think of a case that the grains are all spherically indented into the material, right. So, if I look at the top view, they are all of diameter, indentation diameter d to the workpiece. So, the total area of contact of the work surface per grain that is available will actually be equal to pi d square by 4, okay. And so, this results in pi dHw, because d is root of twice dHw as had been calculated earlier in equation 1. So, therefore, the maximum stress developed in the work surface is sigma w equals the force Fi max divided by Z, so that is force per unit grain, divided by the area of contact of the grain, which is pi d HW. In other words, sigma w, or the total stress exerted by the grain at the indentation point, is given by 8 Fa. This is the average force, okay. This is the Fi max. So, 8 average force A divided by pi Z d HW times of HW plus HT. I am just merely substituting the value of Fi max in terms of the average force as borrowed from the earlier illustration just made a few lines back. So, that is how you can actually record the total amount of stress per unit grain. And so, if it is quite reasonable to assume that the depth of penetration is inversely proportional to the flow stress of the material. And this is so as long as the load and the indenting sphere's diameter remain constant, okay. The load varies or the diameter of the indenting sphere varies, which happens because there is a grain to grain variation in terms of the diameter. Obviously, it changes this approximation that penetration being inversely proportional to the flow stress. So, I am going to now use this probably in the next module to plug the material properties into this equation. So, that now we have everything in terms of material properties and some of the geometric parameters which are involved, and so that is how you find the MRR in case of USM. So, we will do that in the next module. Until then, thank you so much for patiently listening. Thank you.